Chapter 7, Part 5, E2 Eliminations with Cycloalkanes. First, let's take a look at the stereochemistry of the E2 elimination reaction. So the first thing that you have to know about the E2 elimination is that the eliminating beta hydrogen and the leaving group must be in the same plane and anti to each other. Another way to say this is anti-coplanar or anti-periplanar. These words mean the same thing. This is what allows the electrons from the hydrogen-carbon bond to push the leaving group out from behind. Or another way to say that is it allows the electrons to act as a nucleophile in a backside attack. So for example, let's take a look at this Newman projection. The hydrogen and the leaving group must be across from each other so that when the hydrogen is pulled off by the base, the electrons come take the proton. These electrons form the double bond between the two carbons that are represented here, and that pushes out the leaving group. The flow of electrons is all down the same plane. That's really important for this reaction. So the beta hydrogen, the beta carbon, the alpha carbon, and the leaving group must be coplanar or periplanar for proper overlap of orbitals in developing the pi bond. So let's look at this in a 3D line bond image. This first image is what's called anti-coplanar in the staggered conformation, which is what is preferred. And the other example is what's called syn-coplanar, which is in the eclipsed conformation. Some rigid molecules can be forced into this. So let's take a look at an example of E2 in cycloalkanes. We're going to compare two very similar molecules. The only difference between these two molecules is the stereochemistry at the beta carbon. So these two molecules are diastereomers of each other. In the first molecule, the hydrogen and the chlorine are able to both be axial, and this is actually the ideal scenario. The base can come to pull off this proton, and the hydrogen and the chlorine both being axial puts them within the same plane and opposite of each other. So this is the definition of anti-periplanar. So we can form a double bond there and kick out the chlorine. Whereas in our other example, the base would want to come along and grab this hydrogen. But when it goes to do that, the chlorine is not actually in the same plane as those electrons. This hydrogen is, and you're not going to be able to eliminate the hydrogen. So in this molecule, if an elimination were to occur, it would actually occur from this hydrogen here when the chair flip happens and these two are anti-coplanar to each other, both axial. So let's take a look at an example. We're going to compare neomethyl chloride and one of its diastereomers, methyl chloride. Notice that the difference between the two molecules is in the chlorine substituent. The most stable chair form of the neomethyl chloride has the isopropyl group and the methyl group in the equatorial positions. And it has the chlorine in the down axial position. Now this gives us something interesting. There are two hydrogens that are in the up axial positions. Both of these are valid contenders for the anti-coplanar elimination of the chlorine. So if you react with a small base, 78% of your yield is going to come from the elimination of the pink proton because that will give you the more substituted alkene. The other 22% will come from eliminating the blue proton, and this is just the minor product. So the pink product is your major product, and the blue one is the minor product. This means that both of them form, but the majority of your product will be the pink one. So how do we go about solving this type of problem? Well, the first thing you have to remember is that the leaving group and the beta hydrogen have to be axial. Otherwise, they're not coplanar and you cannot do the elimination. So first, ask yourself, does the halogen have an axial beta hydrogen? And then ask, does the halogen have an axial beta hydrogen in the most stable conformation? So let's take a look at methyl chloride. This is the diastereomer to the molecule we looked at on the last slide. In its most stable conformation, the isopropyl group, the chlorine, and the methyl are all in the equatorial position. There is no way to eliminate the chlorine while it's in the equatorial position. So this is the only hydrogen atom that is anti to the chlorine. But if we do a chair flip, we have a situation where there is the axial chlorine and the axial hydrogen. They could eliminate. But in this first one that we looked at, all three of these are equatorial. And in the second one, all three of these substituents are axial. The amount of time that this compound is going to spend in this conformation is almost non-existent. So the chances that this elimination would ever actually occur are slim to none.